The physical world operates in continuous oscillation. When a steel guitar string mechanically vibrates, it displaces the air around it, generating a continuous physical wave of pressure. To analyze that physical event in a computer, we sample it at regular intervals to create a discrete digital signal. We denote this time domain signal as x of n, where x represents the measurement value and n represents the specific time sample index. Whether measuring an audio wave, the daily temperature, or a stock price, these datasets consist entirely of standard real numbers. There are no imaginary components in a thermometer reading or a bank account. The primary goal of digital signal processing is to take that strictly real time domain signal and extract the individual hidden frequencies operating inside it. This visualization shows the standard engineering approach. On the left is our real-valued input wave. On the right, a terminal runs a standard fast Fourier transform. The output array populates with negative frequency bins and complex numbers. The algorithm takes a perfectly real input and generates an output heavily reliant on the imaginary unit I, the square root of -1. This introduces a computational paradox. Since the data collected from the physical world is entirely real, engineers must reconcile why industry-standard algorithms utilize imaginary mathematics to analyze it. To understand why complex numbers dominate modern computing, we must conduct a side-by-side architectural comparison of two different mathematical models, the real discrete Fourier transform and the complex discrete Fourier transform. By tracing the precise mechanics of both algorithms, it becomes clear that the complex output represents a deliberate structural upgrade over real number mathematics. Two analytical pipelines receive the identical real-valued input sequence, 1, 4, 6, and 8. The real DFT uses only real math, producing two separate arrays for every frequency bin. It records the cosine contribution in real x and sine in imaginary x. This architecture forces the system to constantly manage and reference two parallel notebooks of data to represent the phase of a single frequency. The complex DFT fuses this information into a unified complex array. Euler's formula provides the mathematical bridge. E to the I theta equals cosine theta plus I sine theta. The cosine part absorbs the real data, while the sine part absorbs the imaginary data. The imaginary unit I acts as a mathematical spacer. It keeps the cosine and sine values structurally distinct while housing them within the same variable. If frequency bin 4 has a cosine amplitude of 3 and a sine amplitude of 5, the real DFT stores two discrete values. The complex DFT stores them as a single coordinate, 3 plus 5i. This architecture allows the complex DFT to natively accept complex numbers, making it a universal tool for multidimensional signals in radar and radio systems. Euler's formula functions here as a highly efficient data structure. By utilizing the complex plane, a single complex number stores both amplitude and phase. Decoding the values inside that complex array requires fundamentally grounding the concept of frequency in constant rotational geometry. This diagram compares the spectral range for an 8-sample signal. The real DFT keeps bins 0 through 4, truncating the rest. The complex DFT computes the entire spectrum. Junior engineers often discard these upper bins because they represent negative frequencies. In the complex plane, a negative frequency represents a physical reversal of geometric direction. A positive frequency represents clockwise rotation, while a negative frequency rotates at the exact same speed in a counterclockwise direction. Every ordinary frequency is composed of a positive vector and an exact negative partner working together. To reconstruct a strictly real-valued signal, the algorithm must cancel out all imaginary data perfectly. As the two symmetric vectors counter-rotate, their vertical, imaginary movements are perfectly opposite. They sum to 0 at all times, while their horizontal, real components combine constructively. The real DFT ignores these negative frequencies by hard-coding this cancellation into its mathematics, which obscures the full rotational picture. The FFT array's upper half provides the geometric symmetry needed to cancel imaginary data. These negative frequencies act as structural counterweights, keeping reconstructions strictly real. This split affects how amplitude is scaled. A cosine wave with an amplitude of 1 is generated by two counter-rotating vectors, each with a length of 0.5. The energy divides equally between the positive and negative frequency pairs. The DC frequency at k equals 0 and the Nyquist frequency at k equals n/2 both break this pairing rule. Sitting on the real axis, they never rotate into the imaginary plane and have no counter-rotating negative partners. These solitary vectors force the real DFT to use exception-based scaling formulas. It must divide most bins by n/2, but switches to dividing by n/1 for the DC and Nyquist bins. Because the complex DFT maps the entire spectrum, it requires no geometric edge cases. The math scales universally by 1/n for every bin. Algorithms built on uniform mathematics are inherently more stable and efficient in computational environments. Side-by-side comparison shows why the complex DFT has become the industry standard for digital signal processing. It resolves the original paradox by treating real numbers as a subset of the complex plane. A temperature reading of 5 degrees is processed simply as 5 plus 0i. This formatting allows the complex algorithm to ingest real-world data without modifying its actual value. The complex model achieves its superiority by unifying sine and cosine data, mapping the true geometry of rotation, and eliminating mathematical scaling exceptions. From digital communications, automated control systems, and quantum mechanics, all utilize this specific complex framework to model the behavior of waves and rotating fields. Every second, immense volumes of global data pass through this algorithmic pipeline to filter noise, compress images, and transmit signals. The imaginary unit I serves a concrete mechanical purpose by tracking phase and rotation as a single geometric coordinate. This complex architecture allows modern hardware to process the physical spectrum with the speed and precision required for global technology.